So we were talking about the compactness theorem, and maybe I should just give you a So the compactness theorem basically says that a set of formulas is satisfiable if and only if every finite subset. So formulas, let's call it, give it a name, say sigma, every finite subset of sigma is satisfiable. And maybe at the beginning it looks like it doesn't tell us much, but then we saw that there were at least two types of conclusions that we could draw from this compactness theorem. So the two types of conclusions were, one of them was negative, one type was negative, and one type was positive. So negative conclusions had to do with the notion of definability. So we say that, so this is the compactness theorem, then we had this important notion of definability. We said that a set, let's call it W of a propositional truth assignment is definable if there exists a set sigma of formulas such that W is exactly the set of all assignments such that V satisfies sigma. So we talked about this. We had this picture that on one side we had the set of all formulas. On the other side we had the set of all assignments. And here I have some set of assignments W, and it corresponds to some set of formulas sigma, which is, we have this correspondence if these are exactly the set of all assignments that satisfy sigma. So just to make sure that we all understand this notion, what happened if I expand sigma? What will happen to W? If sigma grows, what will happen to W? If sigma grows, what will happen to W? If I look at the set that corresponds to this sigma prime, which is bigger. Yes?
Either stay the same or some elements will be left out.
Right. So if sigma grows, then W shrinks. Right? So note that this mapping is inversely monotonic. In the following sense, if sigma is a subset of sigma prime, it implies that the set of all V such that V satisfies sigma is a subset of the set of all V such that V satisfies sigma prime. Or negatively monotonic, I don't know how you want to call it. Because you can think of the formulas in sigma as some requirements. And these are all the assignments that satisfy all those requirements. So if I add requirements, then even less assignments will satisfy all the requirements. If I have here sigma, which is empty, what will be the set of all assignments that satisfy the empty set? All of them. There's nothing to satisfy. And if I take here sigma to be everything, all the possible formulas, so what will be the assignments that satisfy all possible formulas? None. Because there'll be here some requirement alpha and not alpha. So no one will satisfy all of them. So when this is small, this is big. When this is big, this is small. Yes?
I think you have your sigmas reversed on the...
You're right. You are right. And you got your bonus point. So send me an email for that. Yeah. It's inversely monotonic. Right. If I make more requirements, then I get less assignments to satisfy them. So that's the notion of definability. And the first conclusion, the first type of conclusions from the compactness, so first type of implications of compactness was that certain W's are not definable. For example, we saw that the set of all Vi such that I is in N is not definable. This is where Vi of Pj is true if j is less or equal I, and false if j is greater than I. So this is something we saw last time. That this set of all the assignments that give an initial segment of true and then switch to false, this set is not definable. So we said one type of implication of compactness is showing that certain sets of assignments are not definable. This is a set of truth assignments. Each Vi is a truth assignment. This is a collection of truth assignments, and we showed that this was not definable. And the second type of conclusion was the second result that we saw last time. Second type of implications of compactness was kind of positive results that said, if I have an object, say, so we looked at the question of, the example that we saw here was graph colorability. If every finite subset of a graph G is colorable, then so is G. So this is kind of a positive thing of compactness. Compactness tells me if I want to check if some infinite object has some nice property, it's enough to show that every finite subset has this nice property. Which is kind of the more direct connection to the compactness, because we just build a sigma such that sigma is satisfiable if and only if the graph is two-colorable. And since we know that for satisfiability it suffices to check finite subsets, we can conclude that for colorability it's enough to check finite subsets. But notice that this is two different types of implications. One of them is we can view it as positive, and one we can view it as negative. This one is saying, here are ways to apply compactness to other areas of mathematics. And this is saying, compactness shows me limitations of my logic. Certain things cannot be defined. But the two things are closely related. Why are the two things closely related? Assume that I tell you that I found some way of testing properties on mice that if any property that with my test I will conclude that it holds for mice, I will also be able to conclude that it holds for men. So it's a very useful technique, because then now I want to test drugs, I want to test diets, I want to test all kinds of things. I can test it on mice and then conclude that it's true for men. So it's something very positive. And it says it suffices my tool allows me to suffices to test for mice, I'll get the conclusion for men. But it also tells me something about the limitation of my testing. Because it tells me, for example, that my method of testing cannot test for the existence of a tail. Because if I tested a tail, if you have a tail, then it will hold for all mice, but it doesn't generalize to men. And it's the same thing as compactness. The compactness tells me it's kind of a positive thing. It tells me it suffices to check finite subsets. You can conclude for the whole set. But inevitably, it tells you that you cannot express anything that distinguishes finite from infinite, which is exactly what's happening here. Here we have all truth assignments that give finitely many t's and the rest f. We cannot define it because we cannot distinguish it from the set that gives n infinitely many t's. This nice property that you can test a subset or sub-collection and conclude for everything tells you what you test is limited. It cannot distinguish between finite and infinite. So those two are two sides of the same coin. Now, I want to switch to a different topic, and I know that you're going to be very sad about it. So the comfort is that we will get back to it when we go to first-order logic. As I told you, the structure of this course is such that we start with a very simple language, the propositional calculus. We go through all the typical results that one expects to see in logic in the domain of the small logic of propositional calculus. Then we'll switch to a different language, first-order logic, and repeat the same process. And then we will again encounter this issue of compactness and expressibility, and there the conclusions will be more interesting. So we will revisit this issue, but in the context of a different logic. But the reasoning will be very similar. So I want to switch topics now. You have the assignments to kind of further chew on the topics that I discussed so far. And I want to switch back to the syntax. You remember we said that in the logic we can distinguish two domains, the syntax and the semantics. And we started our discussion by the syntax. We define what are our formulas, what is our language. And we had an algorithm for testing what is a good formula and what is not, all kinds of properties of formulas in terms of parentheses and so on. Then we switched to semantics. We talked about truth tables, satisfiability, logical implication, tautologies, all of those were semantic notions. Now I want to switch back to syntax. And we'll see that those two aspects of the logics are intimately related. So the next notion that I want to talk about in syntax, so far our syntax was very simple, we just defined the language. But in logic there is another very important syntactic notion, and this is the notion of a proof. So we switch to syntax now, and we talk about the important notion of proofs, formal proofs. So we want to build a proof system for propositional logic. And what I mean is that, sure, I'm doing proofs all the time, but I want to talk about proofs within propositional logic. So what do I want to have here? What do we want from a proof system? What is a proof system? What do we need proofs for? So for a proof system, there are three very basic properties that you want for a proof system. So desirable properties of proof systems are the first thing that we definitely want is that if a statement has a proof, then I know that it is correct. It can only prove correct statements. There is no point in having a proof system such that after you see a proof, you still don't know if what you proved is correct or not. That's maybe the most important part of proof system, right? And why did I put correct in quotation marks? Because it's a question of what do we exactly mean by correct, but for propositional logic it will be very clear. By correct we mean tautology, something that is always gets value true. So we want our proof system to be able to be sure that if you prove something, it's a tautology. It always gets value true. But in other logics, the notion of correct can be different. Okay, can you think of other desirable properties of a proof system? Other than that if you prove something, you are sure that it's correct. Yes?
To be able to prove all correct statements?
Right, that's a very ambitious one, but it's a good one. So that would be my number 3. And every correct statement has a proof. That's very desirable. We want a proof system that will, so that while searching for a proof of something, if we can't find a proof, it's not because the proof system is too weak, it's probably because it's not correct. For the second property, people tend to ignore it, but yes?
Is it consistency?
What is the meaning of consistency?
You cannot prove both a statement and its negation.
That follows from here, because it couldn't be that both are correct. So if everything that you prove is correct, you cannot prove something in its negation, right? But so let me alert you to the missing property by proposing a proof system that will enjoy properties 1 and 3. And my proof system is that a proof is a true statement, is a correct statement. So every correct statement has a proof, just the statement itself. It's a proof because it's correct. And if I prove something, it is correct, because my only way of proving is by stating a correct statement. So if I proved it, it's correct. So what's wrong with this kind of proof system? It's
Can't be easily validated or checked.
exactly checked. We need it. We need a need. There is a method, and again, I'll have to put it in quotation marks, on algorithm, which is easy and verifiable to check if a given object is a valid proof. Because if I told you a proof is any correct statement, then it didn't get us very far. Because we didn't know if it's correct or not before, and now we don't know if it's a proof or not. So I need a way of checking whether something is a proof or not. Now, the existence of such a proof system depends on what do we mean by correct and what is our language. So for example, let us start with the simplest example, our example, propositional calculus. Can you give me, we are talking about propositional calculus, and by correct, I will mean a tautology. Can you propose a method that will satisfy all those three requirements for tautologies? So when correct statement means or stands for a propositional tautology, can you give me such a proof system that will satisfy all three requirements? Yes?
A truth table?
Right, a truth table. I'll say a proof of a statement is a complete truth table that contains all possible assignments to this formula, and it is always true. So this will satisfy, so a proof of alpha will be a truth table for alpha that has only t's in the rightmost column. Yes?
So when we're using the verb proof for, we mean that to show that alpha is tautology.
Right.
That's just what we mean.
Yeah, that's what. This is a proof system. It's not a satisfactory. In some sense, it's not a nice proof system. Now, yes?
Why did you say that your first proof system, where a proof is a correct statement, is not efficiently checkable? It's not. It doesn't satisfy two. This one satisfies.
Oh, for propositional calculus, if this is correct, will satisfy two. But if you take say I want a logic that talks about number theory. And I want a proof that there are infinitely many primes. So if I'll tell you what is the proof that there are infinitely many primes, here is the proof. There are infinitely many primes. Okay? So now what is the proof of some conjecture? I don't know. I'll write the conjecture. If it's true, it's a proof. If it's not true, it's not a proof. I don't know. So for the case of propositional calculus, things really trivialize. You're right. I could just say all true statements, and I could check it with a truth table, which will be very similar to what I did here. But in some sense, you have to think about propositional calculus the way you think about Monopoly. And you know the game Monopoly? Anybody knows it? Okay, so in Monopoly, you have monopoly money. I mean, it is supposed to imitate the behavior of the markets and business in the real world. But it is with monopoly money that is not real money, right? And you are just learning the rules of the game. So if I am playing Monopoly against you and I want to have 100 Monopoly dollars, that's very simple. I go to Toys R Us, buy another box, take a pack of Monopoly money. And so this is the kind of cheating that we are doing here. So we should think of propositional calculus as a monopoly that teaches us the rules of playing with logic. But the real intention is to eventually talk about logics that can talk about mathematics, that can talk about programs, that can talk about things that are really complicated. So this kind of trick, truth table, it works only for the monopoly money. It doesn't work for real money. So I want a monopoly money that will imitate the reality, that will look like proofs in real systems, not just toy systems. Okay? So we will not settle for this one. We will look for a different one. One more thing to mention here. So this is one option, but we want an option that imitates the behavior of proofs in the real world. But before I move on, just one thing I have to mention here. Those three requirements are far from being trivial. If by correct, I mean that it is true for the natural numbers. So say I have a language of mathematics that can talk about natural numbers, can say xn is a prime, n is not a prime, there are infinitely primes, there are infinitely pairs of twin primes. You know what twin primes are? Two prime numbers, such a difference between them is just 2. So assume that I have a system that can talk about natural numbers, mathematical properties of natural numbers. It turns out that if correct means it's true for natural numbers, no such system exists. And this is the famous, probably you heard about it, the Gödel's incompleteness theorem. So the Gödel's incompleteness theorem exactly says this. If you try to have by correct statement, you mean a correct mathematical statement about natural numbers, and by method that checks, you mean an algorithm, then there is no system that satisfies all of those, which was a big shock to mathematicians, and we will talk about it more when we get to first-order logic. So just saying, on one extreme, we have propositional calculus in which every trivial thing will have all those three properties. On the other thing, we want to talk about mathematics. Suddenly, it becomes impossible. So we will live somewhere in between. First of all, we will have this toy system for propositional calculus that imitates the way proofs work in mathematics. Then, when we go to first-order logic, we will talk about the way proofs work in mathematics. But if we think about the way proofs work in mathematics, and I think about proofs for number theory, and we prove things in mathematics. So our natural proofs in mathematics, which of those three properties they don't satisfy? Because Gödel tells us, I cannot satisfy all three. But the proofs that we have in mathematics, do they satisfy requirement 1? Yeah, definitely. Do they satisfy requirement 2? Yes, we can check if something is a valid proof or not. So they must fail requirement 3. And that's why it's called the incompleteness theorem. So the conclusion from Gödel's theorem and this shocking revelation that there are statements about natural numbers that are true, but you cannot prove them. Because if you could prove every true statement, you will have property 3. And you cannot have something that has all 3 properties. Okay, so that's Gödel's incompleteness theorem. We will see it later in the course. So for our toy system, we will try to imitate the way proofs are done in mathematics. And the way proofs are done in mathematics usually is that proofs consist of 2 components. One component is a set of axioms, and the other component is deduction rules. How you can move from what you've already shown so far to showing something new. So our proof system, we will just introduce a toy proof system for propositional logic. Our proof system consists of two components. Axioms and deduction rules. And rather than describing abstractly what are axioms and what are deduction rules, let me just go right into the concrete definition, and it will become clear from the definition. So what are going to be our axioms? Our axioms are the set of axioms that we will use for propositional calculus is any formula of the form of one of the following forms. So one is every formula of the type alpha arrows beta arrows alpha. And the second type is every formula of the type alpha arrows beta arrows gamma arrows alpha arrows beta arrows alpha arrows gamma. So it says basically, if you want to read it as if then, if alpha implies that beta implies gamma, then if alpha implies beta, it must also imply gamma. But this is a formalism. This is just a formula of this type. And the third type is every formula of the type not alpha arrows not beta arrows beta arrows alpha. So we have three types of axioms. So let us look at some examples. So I'll give you a formula and I ask you, is it an axiom or not? Say I give you the following formula. The formula says not P arrows Q arrows P arrows not P arrows Q. Is this an axiom or not? So, any volunteer? Oh, brackets, let me make sure. There's a bracket missing here. Yeah, sorry. There's a bracket missing here. Yes?
It's not.
It's not. Why not?
It's not a one of the three forms.
Yeah, I think it is. So why it is, because if we call this formula alpha, and we call this formula beta, notice that this is alpha again.
Is that not based on some step that's required, or is that you can?
Any alpha, that's what I want to say, any alpha and beta. Any formula is alpha and beta. So I can take this to be my alpha, I can take this to be my beta, and this is alpha. The only thing I have to check is that when I take my formula of type axiom 1, and I try to build the parsing tree for it, it first splits by an arrow, and I have something here, I don't care what it is, and then it splits by an arrow again, and I have some object here and maybe some other object here, and the main thing is that this object and this object should be the same. I'll call this object alpha, and I have to see alpha here again. So it is any formula such that its main connective is an arrow, and what you have to the left of the arrow is a formula, and what you have to the right of the arrow is another arrow with the same thing repeating. That's any such formula is axiom of type 1. So how many formulas do we have of type 1? Infinitely many, because I can put any alpha and beta there. And the other thing is that note that it is easy to check if something is an axiom of type 1. I take my formula, I peel off the external brackets, I count brackets, I get to equality, I have to check that the next symbol is an arrow, I put the arrow here, I split it, I keep unfolding the right-hand side, it has to have an arrow, and to the right of an arrow, I have to find exactly what I have there. So it's easy to check if it's an axiom or not, which is important. Okay, let me give you another example. What about P arrows Q, arrows not Q, arrows not P? Is it an axiom or not? We'll have to get used to all three axioms to somehow memorize all three of them. What do you think?
Yes, because 3 will not Q is alpha and not P is beta.
Right, so it looks suspiciously like 3, but it's not.
Assuming we can imply not.
So,
not alpha.
so the whole point here, that's why I'm giving you this example, just to confuse you. The whole point here is that this is completely syntactic. So syntax is just a sequence of symbols. So I look at axiom 3, and I said, okay, it starts with 3 brackets and then a negation sign. Anything, no matter which alpha I will put here, it will always start with 3 brackets and a negation sign. No matter what formula I put for alpha. I cannot get rid of this initial part. And this guy doesn't start with 3 brackets and a negation sign. So it's not an axiom. I have to check that it's not any of the other ones. I have to give you an argument why it's not any of them, right? So I only gave you an argument why it's not axiom type 3. It's not type 3 because in type 3, the fourth symbol is a negation, and here the fourth symbol is not a negation. End of story. The fourth symbol will be a negation no matter what I put for alpha. Why is it not axiom of type 1? Yes?
Because the first sub-expression is not of the...
Right, if I split it, what I get here is P arrow Q. Then I look at this guy. Then I look at this guy here. And when I split it, I get here not Q, and I get here not P. And this guy are not the same. So it's not axiom type 1. Everything is completely based on the checking it symbol by symbol. That's the beauty of syntax. So it's not axiom type 1. Why is it not an axiom type 2? It's kind of a similar consideration. We can say any axiom of type 2 contains at least 1, 2, 3, 4, 5, 6 arrows. No matter what I put here for alpha and beta, I will have at least 6 arrows. And this guy doesn't have 6 arrows. So it's not axiom of type 2. So you can use any kind of syntactic argument that you want, any kind of argument about the format. Just remember that I am allowed to substitute anything I want for alpha or beta. But there are some things which will not change if I substitute alpha or beta. And I will never get rid of those 6 arrows. So it's not axiom of type 2. Okay, so these are my axioms. The nice thing about my axioms at this point, there are 2 things that I want to mention about them. First of all, as we see, it's easy to check whether something, I give you a formula, ask you if it's an axiom or not. You can easily start the parse tree and see if it's one of the axioms or not. The second thing to note is note that each of my axioms is a tautology. It's not difficult to see. Each of my axioms will always get true. Because if alpha is true, then I get here beta arrows true, which is always true. I have true here, everything is true. If alpha is false, then when I have the head being F, everything is true. And it's easy to check that the other axioms are also tautologies. So I have 2 nice properties. They're all tautologies, and I can check what's an axiom and what's not. But still, I have infinitely many axioms. This is not a proof system yet, because this doesn't give me every tautology. Can you give me a tautology which is not an axiom? Because I want to have property 3. I want that every correct statement will have a proof. For me, correct statement means a tautology. Can you show me a tautology which is not one of those axioms? Yes?
A or not A?
Very good point. Yeah, you're right. You're right, but it reminds me of something that I should have mentioned that I forgot to mention. Note that my axioms here use only 2 symbols, arrow and negation. And arrow and negation, the system that contains just arrow and negation, is an adequate set of connectives. So that's not difficult to see that you can express and or with this. And for the sake of proof systems, we will assume that these are our only connectives. The reason is that it makes my life simpler to have less connectives when I have to talk about proofs. Okay? So can you give me a formula which is a tautology and not an axiom, but written only in those symbols, in those connectives? Yes? P arrow P, right. So here is an example. P arrow P is not an axiom, but it is a tautology. Right? How do I know it's not an axiom? It's too short. It has only 5 symbols. Any axiom has more than 5 symbols. Whatever I substitute in the axiom, it will not shorten it. So I know it's not an axiom. It's not an axiom. Just 1, 2, 3, 4, 5 symbols. Every axiom has more. So we know that just the axioms will not do the job for getting me property 3. We want all 3 properties. So now I add a new tool, which is called the deduction rule. So what is my deduction rule? I add the deduction rule. So the second component of our proof system is called a deduction rule that has a name, and the deduction rule is kind of an operation. It takes alpha and alpha arrows beta as inputs and spits out beta. So it kind of tells you, if you already proved alpha and you already proved that alpha arrows beta, you can move the next step and conclude that beta has a proof. And this is called, it has a Latin name, modus ponens. So now we can formally define our proof system. So we say that the set of provable formulas is I of the axioms and this deduction rule. And the rule modus ponens. So we are going to say that a proposition is a formal theorem if it belongs to this set. If it can be reached from the axioms using modus ponens. And so this is the first thing. The second thing, maybe even more meaningful, a formal proof is a construction sequence in this structure. So let me remind you what it means, the construction sequence in IAP. So namely, alpha 1 up to alpha n is a proof, a formal proof. Of some formula beta if each alpha I is either an axiom or the result of applying modus ponens that for short I'll call it MP, to some alpha j, alpha k for j, k less than I. Remember, a construction sequence for IAP was a sequence such that every element is either an element of A or you got it from the previous ones by operation in P. Our operation is this modus ponens, so let me write it here. The rule MP is the rule that takes alpha and alpha arrows beta and deduces beta. Yes?
Modus ponens is kind of specific. Like it says if alpha and if alpha implies better than beta. Do you also allow for like proof by computation where we say?
No, only this, right? It is a very limited system. It's a kind of toy system. So let us show you a first example of a proof in this system. It looks like it is a very limited system, but it really imitates the way proofs work in mathematics. So here is the first example. Let us prove that for every alpha, the formula alpha arrows alpha is a formal, how do you call it? Is provable. Alpha arrows alpha is provable. So how will we do it? I will write a construction sequence. My first element will be alpha arrows alpha arrows alpha. Why am I allowed to start my sequence with this? Yes.
It's an axiom,
Which one?
number one.
Right. This is axiom 1. Now I can write alpha arrows alpha arrows alpha arrows alpha arrows alpha arrows alpha. What? No. No, no, no. I think I have to start with something more complicated than this. Right. Okay, so I'll start with a different axiom 1. I'll start with alpha arrows alpha arrows alpha arrows alpha. Okay. This is still axiom 1 because I have here alpha arrows beta arrows alpha. It's still axiom 1. Now I will write the following. If alpha arrows this guy, alpha arrows alpha arrows alpha, then if alpha arrows alpha arrows alpha, then alpha arrows alpha. Okay. Yeah, no, it's completely confusing, but it's just a very simple game. Like to check if something is a proof or not. So why am I allowed to write what I did now?
Axiom 2.
This is axiom 2.
Also one close bracket.
I'm sure that I missed tons of
You're
brackets.
short one close bracket at the end.
Yeah?
That's it.
Right. Okay. So why is it axiom 2? Because I can call alpha, call it A, call this guy B.
No.
No. Call this guy B and this guy C. So I have here A arrows B arrows C. And here I have A arrows B arrows A arrows C. And this is the structure of axiom 2. If A arrows B arrows C, then A arrows B arrows A arrows C. So this is axiom 2. Now, what can I do now? Now what I can notice that the head here is the same as what I have here. So if this is my alpha 1 and this is my alpha 2, alpha 2 has the form alpha 1 implies something. So now I can use modus ponens. Right, so call this one alpha 1, call this one alpha 2, and now we apply the rule MP to alpha 1, alpha 2, and get, see, I have here some formula, and the same formula is the head of the next one. So what does the modus ponens tell me? I can just delete the initial segment and be left with the right-hand side. So I'm left with the right-hand side, which is alpha arrows, alpha arrows, alpha, arrows, alpha arrows, alpha. Right? I'm left with this part. The modus ponens told me if this and this are the same, I can delete it and be left with the implicant. So this is my alpha 3. Now, how can I move on? I wanted to get to alpha arrows alpha at the end. So can anybody see what will be my next step now? Yes?
So left side is an axiom.
Right. So I will write alpha arrows alpha. And this will be my alpha 4. And this is allowed because this is axiom 1. And now I have alpha 4 and alpha 3 just ready for feeding into modus ponens. So I'll say apply MP to alpha 3, alpha 4. I can cut this, and I'm left with alpha arrows alpha, which is what I wanted to reach. So what we can already see, I mean, we are going to show that our proof system really satisfies all the 3 requirements that we had. One, it is everything you prove is a tautology. You can check what is a proof and what is not, because you can go step by step and check if it's an axiom or it is the result of modus ponens to previous guys. And we'll even show that you can prove every tautology in this system. It still lacks one requirement that I didn't write down, but is very important in mathematics. And that the fact that in many cases in mathematics, a proof is a way of, has an explanatory value. Proofs explains to us why something is correct in many cases. And these proofs don't explain anything. It's not that when you see this proof, you will say, oh, that's why it's correct. Because when you see these proofs, we can say, okay, so someone was bored enough to work out all those proofs. I mean, I have a collection of proofs that I build up over the years of teaching logic. But each time I have to teach this class again, I have to go back to my list and revise the proofs, because there's no way you can derive them. I mean, if I want you to fail an exam, I'll ask you to do some formal proof. That's a sure way. So it doesn't have, and usually in mathematics, you want to prove something, you think to yourself, let's try to understand why it is correct. And then let's formalize this understanding into a valid proof. This system doesn't have this value, but it satisfies the other properties, so it's for us a good toy system to demonstrate what can be expected from proofs. Okay? So let me just recap where we are now. So we have a notion of a proof system. It consists of axioms and MP and the deduction rule. And it has the structure that I promised you is going to repeat over and over in the course of an inductive definition of a set. There is a core set, there is an operation, and we apply this operation over and over again. And a formal proof is a construction sequence in this IAP. My A is the axioms, the P is the modus ponens rule. And I think that before I go on, I'll show you another example, and I just have to remind myself of the other proof. I wrote it down. Okay, so let us, for example, do another one. Show that, one thing that I want to add is notation. So a bit of notation. We will use this T, lying down T, to denote formally or proofs. So this denotes alpha has a formal proof. Or alpha is provable or whatever. So we'll use this notation. And now I want with this notation to show you another example. And I want to show you that for every alpha, you can prove that not alpha arrows alpha. Do I have enough? Yeah, I have enough brackets. So I want to show that double negation arrows can be deleted. The double negation can be deleted. And again, to check its tautology is trivial, but you want a formal proof. So how are we going to do it? We're just going to do some gymnastics. And I'll now be very lousy with, very loose with brackets, because otherwise it's going to be more crazy than it really is. So my first step is I'll write 3 negations alpha arrows 1 negation alpha arrows 3 negations alpha. Why am I allowed to write this? It's axiom 1. Note this is axiom 1. Because you just have this format of something, arrows, and I have an implication where the first something appears at the end of the arrow. Okay, now, if I have an implication, I can I'll write axiom 2. So my axiom 2 will say 1, 2, 3 alpha arrows 1 negation, 3 negations alpha arrows 3 negations alpha arrows 1 negation alpha arrows 3 negations alpha arrows 3 negation alpha. So why can't I write this? So this is axiom 2 because there's no way to follow what's happening now if you missed the beginning. We're playing a very weird game. So this is A. Sorry. This is, I can read it as follows. This is A. This is B. This is C. So I have A implies B arrows C implies that A arrows B implies A arrows C. So this is axiom 2. This is just axiom 2. Now, all I have on the board are 2 lines. This line and this line. But what can I do with these 2 lines? I can do modus ponens. Because all I have to notice is that the head of this implication, is the same as what I have here. So I can do modus ponens. I have an alpha there, and I have an alpha arrows beta here. So I will use modus ponens, and what will I get?
The right side is also.
The right side. So I'll get 3 negations alpha, arrows 1 negation alpha, arrows 3 negation alpha, arrows 3 negation alpha. Now, once you get some familiarity with axioms, you will see what this is kind of calling for. I have arrow, arrows, arrow, and I have tons of negations around. So which axioms looks most likely to be used now? 3. So what will give me I'll write a case of axiom 3. I'll write this is the head of axiom 3 and something is the tail. So axiom 3 will tell me if I start with this guy, 3 arrows 3, and axiom 3 tells me I can delete 1 negation from each. 1 negation from each and reverse the order. Am I okay or not? So axiom 3 tells me I can delete negations. If I have here not A arrows, not B. Sorry. No. What am I? Did I confuse myself now? Yeah. Not arrow, A, no. Yeah. It implies alpha. It implies. This is. No. How did I get myself confused? Just 1 second. I knew it's going to happen. No, sorry. I will not. It's too much for me to do it on my feet. So let us move on. So let us move on to the next step, and I will finish it next time. I'll come with its whole. I wrote an outline for myself, but it's not sufficient. It's too confusing. Okay, so let us just leave the completion of this to the next time and see where we are. So now what I want to show, we have 3 requirements from a proof system. Requirement 1 is that everything that I prove is correct, and correct for me is a tautology. Requirement 2 is that it's checkable. Requirement 3 is I can prove a tautology. We already saw requirement 2. Let us show requirement 1. So this is a theorem. And it has even a name. It's called soundness theorem. And it says the following. It says that for every formula alpha, if alpha is provable, then alpha is a tautology. Now, how are we going to prove it? Since it is a statement about all provable alphas, and provable alphas is a structure of IAP, the proof is going to be by generalized induction. Proof by generalized induction on my structure, which is I of axioms MP. So what is the base case? What do I have to show for the base case? I want to show that everything in this structure is a tautology. So what is my base case? Right. Base case is just check that every axiom is a tautology. Right? And that's easy because this is just, each of them has a very simple truth tables regardless of what is alpha and beta. Each of those are going to be a tautology. So let us assume that we can do it ourselves, I mean yourselves, and let's go to the induction step. What is going to be the induction step? What do I have to assume?
Alpha is topology and beta is topology.
No.
Alpha is a provable guy and beta is also a provable guy.
No. Think a little bit and come up with the correct. I take this as components and generate this. So if my conclusion holds for the components, I want to show that my conclusion holds for the outcome. So the induction hypothesis is assume that our conclusion, alpha is a tautology, holds for the input. So we assume that both alpha and alpha arrows beta are tautologies. And what do we need to show? Under this induction hypothesis, what do I need to show? That the outcome, right, that the outcome is a tautology. That beta is a tautology. Okay. Now, maybe the easiest way to show it is to go by way of contradiction. So let us go by way of contradiction. Assume that beta is not a tautology. Right? So by way of contradiction, assume beta not a tautology, which means that then for some truth assignment V of beta equals false. There is an assignment that makes it false. Right? Now for this V, what is V of alpha? What is V hat of alpha for this V? Why? Because alpha is a tautology. This is true since alpha is a tautology by our induction hypothesis. But now what happens to alpha arrows beta? So what do we get for V of alpha arrows beta? We get true here, false here. It will be false. And that's contradicting the assumption alpha arrows beta is a tautology. Yes?
Since we're using contradiction here, can you sort of say that the system cannot prove its own soundness?
What?
We're using contradiction here, which is not part of our formal proof method.
No, that's a good point, but you have to be careful. We are doing real proofs in mathematics. We are talking about formal proofs. But we're not doing a formal proof because I'm writing in English. A formal proof, I'm just writing lines of formulas. Now what we did is we took real money and bought a box of Monopoly. And there was a statement like saying, every Monopoly game is square. It was a statement about the game. It was not playing the game. Okay? And one last comment, notice that we made the first connection between syntax and semantics. Because in syntax, alpha has a proof is a syntactic notion. Alpha is a tautology, is a semantic notion. So we made here our first connection between these two aspects. We show that whenever alpha is provable, then alpha is a tautology. Okay, so we will continue on Thursday. Thank you.